So, as promised, let's start our story by figuring out what the Sun had to do to become a main sequence star. We're going to follow the models. The models are going to start with a spherical cloud with, say, one solar mass of gas and dust in it. And this is already fragmented, possibly, from an even bigger cloud. We'll talk about that when we talk about the formation of clusters. We're now building a star. This cloud is collapsing under the influence of gravity. And what the models tell us is that within a few thousand years, the interior of this cloud becomes dense enough that there is an optically thick, opaque region there. This is great. This means that we can define the interior of this region as the protostar. The protostar has a surface. It communicates with the rest of the world through blackbody radiation. We can plot it on an HR diagram. At this point, we've produced, if you want, a nascent photostar. This photosphere will start out at a size of about 5 astronomical units and a comfortable temperature of 300 Kelvin. And now, what the models tell us is that this thing is contracting and, of course, heating. And you compute the luminosity. It remains approximately constant over a contraction from 5 astronomical units all the way down to about twice the current solar radius. Again, what's contracting is the surface at which the protostar is opaque. Some material, of course, is penetrating. This is still accreting. The protostar is still growing in mass, and the energy to heat for this heat is, to some extent, Kelvin-Helmholtz heating, conversion of gravitational potential energy to heat, but also at these temperatures we begin to get fusion of deuterium. Whatever amounts of deuterium are present, the deuterium fuses at a lower temperature than hydrogen. That's why we use it in terrestrial fusion reactors. And over the next 600,000 years or so, we get this collapse down to twice the solar radius, and the temperature stabilizes at around 4,000 Kelvin. These early stages are built on models. We can try to verify them by looking for these very young, very cool protostars. This used to be a very difficult proposition because when a protostar starts forming, around it is the leftovers of the big cloud, the parts that did not collapse yet. So there's this gaseous, dusty cocoon that hides the protostar. To look through the dust, we use radio and infrared radiation. And in recent years, we have had detections of these early stages of protostars. You can learn a lot from the intensity in various wavelengths, the shapes of the absorption and emission lines. Too much detail for us, but here's a nice direct imaging of these 3 nascent infrared sources, luminosities 1 and 1,000 and 1,000 solar luminosities and 100,000 solar luminosities. These may be as young as 100,000 years since they started collapsing, so they are fueled by Kelvin-Helmholtz heating and by the beginnings of deuterium burning, and these photospheres are the dusty, hot, opaque regions that we were talking about. This is a magnified image, and it shows you that the IRS-9A, the 100,000 solar luminosity protostar, is 5,000 astronomical units across. It's a very large object. Still, it's just beginning to collapse. Another interesting object is this one, L1527 in Taurus. And here we're seeing edge on the disk in which the star is forming. So if we had a protoplanetary disk, it would extend this way. And what we're seeing is these bipolar flows of gas leaving. This is an infrared image from the Spitzer telescope. And here we have a magnified Spitzer image which shows you that actually we're not seeing the protostar in the infrared. In the infrared, we're seeing reflected light off the disk, and the center where the star would be, the disk is so optically thick that it actually obscures the star. The contours that are actually showing us the position of the protostar inside this few hundred astronomical unit disk are radio emissions. So superposing radio along with infrared, we can see both these bipolar flows that we'll talk about later and the protostar itself. So we have now actually seen protostars. We know that they exist. And when the protostar has reached the point at which its size is about twice the solar radius, its temperature is about 4,000 degrees, and deuterium is burning, we now call this a pre-main sequence star. There is fusion that is fueling the star. And so we begin to plot the trajectory of the sun as a pre-main sequence star on the HR diagram. The protostar phase was this horizontal trajectory that the sun followed. And what we see initially is that having become a star, it's burning deuterium, so it's sustained at least partly by fusion. It's still contracting, and the contraction is along almost a vertical line. This vertical line is called the Hayashi track. The temperature is determined by the fact that the photosphere is no longer made of dust. Dust has long since evaporated, where it's 4,000 degrees. What makes the photosphere optically opaque is the presence of negative hydrogen ions. Negative hydrogen ions, that's a proton with 2 electrons. The extra electron would have come from ionizing metals, calcium, silicon, carbon. They have outside electrons that are more weakly bound than the 1 electron of hydrogen. They become ionized at lower temperatures as positive ions. Some of these electrons will be captured to produce negative hydrogen ions. Negative hydrogen ions are excellent absorbers of radiation at all wavelengths because the second electron is rather weakly bound, and infrared, visible, and certainly ultraviolet radiation will ionize, or deionize. And so negatively charged hydrogen ions are a great light valve. A layer of those absorbs all colors of light. This is now our photosphere and then re-emits it as black body radiation. And so this photosphere contracts, and its temperature is controlled by the ionization state of hydrogen. And so it contracts essentially along a line of constant temperature. And this continues. You notice at constant temperature, the star is contracting, therefore its luminosity is decreasing, until the ionization in the center becomes, as the center heats, the ionization in the core increases. This makes the core less opaque. This allows a radiative zone to be produced. This makes the efficiency of transporting heat out of the core into the envelope higher, and that increases the luminosity, and that is this knee in the track that we see around here. This is this increased ionization, and this continues to proceed until temperatures in the core reach sufficient temperatures and densities are such that hydrogen fusion starts. What happens when hydrogen fusion starts? Well, what happens is that the core ceases to contract. In fact, under the increased radiation pressure, it expands slightly. The expansion of the core absorbs some of the energy that's produced by fusion, and so the initial response, this is one of those, expansion by contraction in reverse. When the fusion is initiated in the core, the reaction of the envelope is that the luminosity decreases, and that's this final segment of the track. So this turn here is the initiation of efficient hydrogen fusion in the core, and the star now settles down by a loss of luminosity down to the main sequence. It would have taken the sun, models tell us, about 40 million years. Remember, this was a few 100,000, then this track takes about 40 million years, and the sun settles down into main sequence equilibrium. That time scale is familiar. 10 million years was the Kelvin-Helmholtz time scale. That is how long the sun would have produced its current luminosity from gravitational potential energy, and 10 million years is the time scale on which gravitational energy is converted to heat, and we'll come back to that time scale. Emboldened by our understanding of the sun, we can repeat the models with stars of different masses, and we find these tracks. They all, if you notice, start, though it's not obvious in all of them, with approximately the same Hayashi track, where negatively ionized hydrogen controls the temperature, and then move over to the left, heating up and contracting for more massive stars at almost fixed luminosity. All kinds of details. They settle down to the main sequence. As we saw with main sequence lifetime, the models tell us here that bigger stars go faster. So the sun took 40 million years to achieve its current main sequence, or to arrive on the main sequence. A star with a mass of about 5 solar masses would take 1 million. A star with a mass of 15 solar masses would take 100,000 years. And stars with 30 solar masses would get to the main sequence in tens of thousands of years. So that when a cloud forms, the first stars to reach main sequence are going to be the hot O and B stars, and the lightest stars will be the slowest ones to go. So we have seen how cloud collapses down to a star. We spoke of the lightest and the heaviest. What makes these the lightest and those the heaviest? What happens if you start with a cloud that is too small? What happens if you start with a cloud that is too big? Why does the main sequence end? The mechanisms of star formation should tell us, and they do. First, below about 1.3% of a solar mass, deuterium fusion never initiates. If an object never initiates deuterium fusion, its collapse mechanisms are different. We do not call that a star. It's also true that the fragmentation processes that break the clouds up seem to stop at about 1% of the solar mass. So we do not expect stars to attempt to form much below 1%. But below 7.2% of the solar mass, efficient hydrogen fusion never takes off. And so these stars do not achieve hydrostatic equilibrium under hydrogen burning conditions. So they do not become main sequence stars. They take their time contracting and burning deuterium. They run out of deuterium earlier. These are brown dwarfs, type L, T, and Y. These are the extra spectral types below K that were added. They were added by models. The first actual discovery of a brown dwarf is relatively recent. It's 1994-95, when this object, Gliese 229b, was actually discovered, both by Palomar and by the Hubble Space Telescope. And after that, infrared surveys started showing that there were brown dwarfs in the solar neighborhood. People started extrapolating those surveys to imagine how many brown dwarfs there were in the Milky Way, and the going rate about a decade ago was that there was one brown dwarf for each main sequence star. So at that point, the estimate of the number of stars in the Milky Way essentially doubled, because there was going to be as many brown dwarfs previously undiscovered as there were main sequence stars. More recent data has cast doubt on this. We found sort of a collection of brown dwarfs. We've gotten rather good with these infrared surveys at discovering them. And a recent survey by the WISE detector of the solar neighborhood, a tally of these, the calculation of the efficiency at detecting them, suggests that it's more like one brown dwarf for each 5 main sequence stars. Number of stars in the Milky Way has again decreased. Science is a succession of approximations to truth. This is what cuts off the main sequence at the bottom end. Objects lighter than 7% of the solar mass will never actually manage to heat and be hot and dense enough at the core to initiate efficient hydrogen fusion. What cuts you off at the top end? Well, if you start with a cloud that is too big, it will not actually manage to make a star. As it collapses, radiation pressure will break it up. We might talk about the Eddington limit that gets involved here later. But again, a few years ago, I would have said masses bigger than 100 or 150 solar masses cannot possibly form a star. That is what models suggested. And indeed, stars with masses as high as 100 solar masses are exceeding rare. But it turns out that again, observations come to the rescue. In the Tarantula Nebula, in the Large Magellanic Cloud, 2010 discovery shows, well, here's a visible image of the Tarantula Nebula and a magnified visible image of the Tarantula Nebula, and over here on the right, an infrared image which gets rid of all the scattered light from dust and sees through the dust. And among these stars that we're discovering, these main sequence stars, is this monster object R136a, and R136a has a mass estimated at about 250 solar masses. And for a size comparison, we see here the Sun, O-type star perhaps, and then this new monster. So the current limits are that stars can form with masses up to about 250 solar masses. This is still very, very rare. Above that, radiation pressure will fragment the cloud. So we understand what the main sequence is and where these stars come from. We'll pick it up at the end of the main sequence lifetime in the next class.